Where?
Oh, so
Yeah. Where is it? Here. Yeah. Should be recorded already. Yeah. Okay, good. Okay. So during lesson 6, which is before your turn break, right? We talk about piping system, right? So for the next maybe half an hour to 35 minutes, I will share with you like sizing. Now you know that the pipe systems goes to whatever, right? And we do some sizing. Then we'll go through the tutorial. Not go through, actually, I will share with you the tutorial. Then you try to do maybe at least 2 to 3 questions on the tutorial. Then we will then end the lesson for today. Okay, can right? Okay, so for piping system, we have done this before. Just want to repeat a little bit. There is a condenser circuit. Green color, remember, I try to let you know that green color is like outside, right? So green color condenser circuit, right? It can be through type. That means you just flush out the water, let it cool down like shower. Or it can be open type. You circulate, go to the cooling tower, come back. All right. So this is through type or open. Okay. And then chilled water is the one with the fan coil, right? Fan coil or some cooling coil. This is the closed type. Okay. So two types. So piping configuration, direct, reverse return, and ring loop. Okay, direct, go straight, supply, bypass, come back. This is direct. Reverse, actually, because reverse return is just to add another line here. Then there's a return line, very similar to the direct, except that the direct has a two-way valve. Reverse return actually also have a valve, but it actually has additional line. That's the only difference. Okay. This is the one that we usually do right now. If I think most of you are in FM, if you go to your chiller system, right, you see the chiller pipe go up, then they either go one round and then come back. So it's usually the loop system, especially a lot of newer commercial buildings like that, except the older one. Unlike from like hotel, right? Hotel, one of the branch goes up, then there's a AHU, and then usually one floor has, anyone know one floor has roughly how many AHU? Usually two, yeah, very good. Usually have two AHU. Okay. So chilled water type, there's a constant flow, variable flow, and then secondary and the primary circuit. There we talk about constant flow, how it runs, and variable flow, how it runs. But this is for the chiller. I think one of the team is doing the constant air and the variable air volume, right? So a very similar concept, except this is for water. Then two-way bypass valve goes in, differential pressure is here, and it kind of bypass. So we did this. We talk about the circuit for chilled water is a primary or a separate set of distribution system, which is a secondary loop. Then variable pump can be used for secondary and primary circuit. Then we talk a little bit about we talk a little bit about how the whole system look. Then I share with you, like, let's say the first system return is 10 liters per second. First evaporator can be 10 liters per second. Then it goes to a primary pump, or secondary pump can go to somewhere else. So this is like how the one of the systems can look like. And we also share about chilled water expansion tank. Usually, right, you're allowed for expansion of water, point to add water, and there's open type and closed type. So the chilled water expansion tank, make up water goes in, just like our flush toilet, right? There's a floor ball that floats up and down, and then water goes in. There's an overflow pipe, sometimes to the drain, overflow, and then there's a pitch. So open chilled water expansion tank, right? It's usually placed on the top. So like there's some gravity or some head that is able to go through the cooling coil. So it's a chilled water expansion tank. Can have a compressed air diaphragm, and then basically how you push back. Then there is the expansion type. And we talk about pipe insulation. right? Insulate, pre-installation or on-site installation. Then we talk a little bit about, hey, it's on-site installation, you have your pipe, then some kind of fiberglass or wood material with aluminum foil and a steel jacket. Then there's some jacketing. But most of the time right now, we try to do pre-insulated pipe, right? So it's in Singapore, it's labor cost is a little bit more expensive. But let's say you're working in some other country project, the sheet metal jacking is still quite popular lah. Right. Okay, so water condenser circuit, we talk about this. Water condenser, okay, supply. Sorry, this is usually the return. Return is usually higher. We try to remember by supply, everything supply temperature is lower. So from cooling tower, you supply 29 degrees, pump through the pump, go through condenser, then this is the return, sorry, this is the return, right? 34, then go to the cooling tower. So this is the condenser water circuit. And the principle for circuit design, right? So there's now 9 principle. Okay, so what we need to do is centrifugal force must always be prime, right? That means you must put water inside the pump, right? I think I shared with you when you during your first practical, right? I talked to you a little bit about how centrifugal pump looks like. And basically you need to prime out. Centrifugal pump is something like you have a string, you throw a ball. So the longer the string, the further the strength it is, because force equals to mr square, right? So mr omega square. So you actually longer the distance, the stronger your force is. Okay, so centrifugal pump must be primed because you need to fill up the pump, then it can actually run. Then cavitation must be avoided. Cavitation is like an air pocket. Right? So imagine you have a small stone. If you have a small stone, if your radius is very small, it's not so painful, but you tie a string, right? And then you swing, the strength of this small stone become very, very strong, right? So very strong, meaning to say if your centrifugal force has air bubble inside, and the air bubble is being pushed to very far, it's just like a small stone with a string, then the force is very high. This is called one of the acronym is called cavitation. Okay, cavitate, just like it actually erupts some of the pump. So there's more water inside, cavitation happens, sometimes your pump will get corroded or eroded, sorry, easily. So then air must not be drawn to the system, air vent, then open circuit, right? And we talk about now the design of the circuit. All control valve must be below static water level in open circuit. Attention must be paid to the positive head. Okay, so that you have open vent, then you have the risk of water being boiling. If not, water keep changing, right? Then it basically will have a problem with your water. So all the valve must be below the static water level. So at least it can flow, right? The connection from a feed expansion tank must be placed at one place so that the principle are then followed. Okay, so right now what we will do is basically how to do pipe sizing. So just now what we mentioned is the lesson number 6. So today we'll share a little bit more about pipe sizing. So pipe sizing, in order to size the optimum pipe, we actually will have initial cost, and of course the OMM, operation maintenance cost, plus water velocity and pressure drop. Okay, pressure sizing, small pipe has higher velocity and pressure drop. So it's just like you're watering the plant, right? You have a hose, you have a small pipe, you close the pipe hose, right? Then what happened? Your water suddenly like shoot out, right? So smaller area, higher velocity, and then your kind of the pressure will drop. So high water velocity, right? You'll have noise problem. Okay, and then you will have erosion. If you have high pressure drop, then your pump will increase its operation cost and you need to have a larger pump. So in short, pipe sizing needs to vary the size of the pipe. The smaller the pipe, the higher the velocity, and there is also high pressure drop. Okay, then if you have very high velocity of the pump water, the water move very fast in the pipe, then you have noise problem. If your pressure drop is very high, and suddenly there's from maybe 10th floor, your water suddenly go down to maybe first floor, then your pump need to push, or you need to have your pump work harder. When your pump work harder, the operation cost of your pump increase, and you need a bigger pump. Make sense? So these three kind of component when you're sizing a pipe, sizing a pipe. So water velocity permissible is what are the things that water velocity is able to do or permit to do. Maximum velocity needs to be established by the noise generated by water flowing through the pipe, and then erosion of the pipe by water entering like sand or air and foreign particle. So erosion, we usually use a filter or strainer to take care, right? Right, but noise sometimes very difficult. Noise sometimes is very difficult. So there are later I'll show you a chart. So in order to avoid this noise, right, all the engineers or the guys that actually design a pipe actually give you a range, which velocity choose which pipe, so become easier. Okay, just like a template that you can do. If you need maybe 5 meters per second, then they give you a pipe. So with all this, we reduce like the noise generation, we can reduce erosion. So that is like the design parameter. Okay, we'll learn a little bit on that, how we do that. So minimum water, okay, just now we talk about maximum velocity, right? Then now minimum velocity. So you need to keep any air inside, need to keep any air which tends to collect certain parts in the system moving. So all the air pocket, you need to kind of let the air move. Okay, so if there's a trap in the air, sometimes we call it dead space, right? Then the air will then create, although it's air, it's just like our blood vessel. So what happens if more and more velocity flow, air becomes trapped, and then that will create some problems within your pipe. So we need to prevent sediments from settling in the pipe also. So that's where the filters or strainers comes in. Okay, friction loss. Once through the system, it must be able to have a flow so that you have minimum friction loss or pressure loss. Then it can then be reduced. Then recirculating pump are sized to provide reasonable balancing, right? So that the pumping power due to high friction loss and increase of piping costs due to the pipe sizes. So we also need to allow aging. That means a pipe will age, right? So we will increase usually the thickness or the roughness of it so that it reduce the aging. We take care of the aging, and then we design for excessive age. So we allow a little bit of additional capacity. Okay. So sizing method, what we are going to do is we are going to learn a method called equal friction. Equal friction. So what do? We need to prepare a piping system. Then we find the flow rate of the section. Then we choose the friction loss rate from the main pump of the following. Yeah. So we learn this method called equal friction. So instead of calculating the distance, how many bend and stuff like that, right? We say that, hey, turning a bend is equal to certain friction, or going up a hill is certain friction. Then we collect all together and then say that with this friction, right, you need to have an additional range of velocity or pressure. Okay, make sense? So recommended velocity is about 120 mm, right? The diameter, if it's about 125 mm, right? 125 mm is about how many inch? This is about 5-inch pipe, right? About 5-inch pipe. Then the range of the velocity should be about 2 to 3.6 meter per second. And then if your diameter of the pipe, right, is 50 to 100 mm, so 2-inch pipe to about 4-inch pipe should be about 1 to 2 meter per second. Then if it's less than that, small pipe, right, then your velocity should be around 0.5 to 1. Usually, so many parameters, how to remember. An easy way to remember for me is the pipe. Usually, if you can around 2 meters per second, 1 to 2, then that would be pretty good kind of sizing. Okay, if forget everything, right, because there's a range, 2 meters per second would be easily a good size to kind of size your piping. Okay. So sizing method, you can select the pipe from the pump, then from the friction loss chart on the limit, and there's more than one choice, you select the smaller pipe. The initial cost will be more critical, and then continue along the circuit to select the best piping. Yeah. So sizing method, what we are going to learn today is equal friction. So when flow rate decrease, right, the next selection smaller pipe size from the chart so that the friction loss rate is approximately equal to the value chosen. So do not let the velocity decrease below 0.6 meter per second to prevent dirt or air settling. And you select the pipe branch in other circuit, right, so that it is not extremely short. Okay, sizing method also use a smaller pipe size in this branch so to create an increase in pressure drop. So let's say you have a big pipe coming in, then you select a smaller pipe that will actually help on this problem. So determine by inspection and the longest or the greatest equivalent length, then we calculate the pressure drop in the circuit. Okay, so then we want to prepare for chilled water piping. We can prepare the water schematic drawing. Then what is the accumulated chilled water flow? And then we, like a ducting system, we can then size it. And with some head loss in the index, then we can then calculate the total flow of the chilled water pump. Okay, condenser water pump is, condenser water piping is a similar approach, except that now condenser, right? Condenser, you see, always goes to the cooling tower. Condenser water pipe, right? It's kind of similar procedure, which is comprising of the condenser, like refrigerant machine. Okay, all these criteria, right, is based on SS 553, Singapore Standard 553/2016. So like Crossfire talk about, hey, what's the design parameter? Okay, and then pumping system should not exceed 7.5 kilowatt and then should comply to 10.7.2 or 10.7.5. Then pump power should be about 349 kilowatt per meter square per second to about 301 kilowatt per second. So that's limited within the chilled water system and the condensing system. Okay, then motor exceeding 3.7 kilowatt should have some control. Right? This is based on the criteria. Then not more than 30% of the wattage at 50% of flow. So in short, when you want to design motor, it must, when it exceeds 3.7 kilowatt, it need to have some control. And finally, section 16 talks about the general piping part. Okay, so this one looks super complicated, right? But no worries. Okay, so let's take a look first. If you look at, okay, so if you look at this chart, right? Right, the one with the light blue is the water velocity line here. Okay, which is one slide here. The green one is basically the pipe diameter. Okay, and this is the pressure drop. Okay, pressure drop is on your y-axis. So 50 to 3000. A good range is actually the yellow color range, right? So then the volumetric flow in liters per second, right, will be at your, what do you call that? At your x-axis. So this is for a Schedule 40 commercial steel pipe. Schedule 40 is basically you got Schedule 20, Schedule 10, Schedule 40 is the thickness, one of the thickness of the pipe, right? And so let's see. So assuming take it easy. Assuming your volumetric flow rate is 20 liters per second, after you calculate 20 liters per second, right? Then you basically follow this line up. Okay, and then you would like to have a water, maybe your water velocity, okay, 20, right? Water velocity about 1.6 meter per second, right? So water velocity about 1.6 meter per second, your volumetric flow rate is about 20, then our pressure drop approximately, right? Oh, sorry, the pipe diameter we need to choose will be approximately about 125 mm. That means a 5-inch pipe. Okay. Not still able to do. So 5-inch pipe at this particular point, your pressure drop will be approximately about 200 Pascal per meter. So not so bad. So in short, this yellow color part, right, is a kind of what do you call that? A area we try to select a pipe. Okay, right. So equivalent pipe is what? So let's say you have a gate valve. A valve is like that, right? So a gate valve, equivalent length of a pipe is like given the same length. So when you go through the gate valve, right, if there is friction, okay, instead of calculating the valve, what we do is one gate valve is in approximately about 0.75 meter. What does it mean? So assuming you are queuing for the, what do you call that, the if you're going to JB, right, then you're trying to go through the custom. Custom have a gate. Gate will increase. The people will be going through the pipe slower, right? So just imagine this gate, instead of putting one gate to control the cloud, one way is to increase the queue. Okay, make sense? So instead of I put a gate, I slow down the people, I make the line longer, right? Make the line longer, people will be able to queue more, correct? So the same concept that we use, the same concept to do this is called equivalent length. So a gate valve, approximate equivalent length is about 0.575. Okay, so equivalent length, right? For tight fitting, what we can do is usually given the length, there's a diameter. So there's an equivalent length, which we usually use it as L subscript E or LE. LE divided by D is virtually what we call a constant for that fitting. Okay, so approximately if you have a LE for 100 mm group valve, right? So L over D is about 320 times the diameter will be about 32 meter. So LE, right, of a what do you call that? 100 mm meter graph will give you about 32 meter equivalent length. Make sense? So another word, if you have a gate, assuming a gate, if you have a gate of about 100 mm, right, instead of controlling the cloud, right, it will be equivalent to about 32 meter of additional queue line you need to let queue. So that's another way to think of it. Make sense? So why do we want to use such method? Because it's very difficult to say that, hey, this is 100 mm group valve, and then sometimes number of gate will kind of confuse, right? Not say it will be very confusing because there's gate valve, there's what do you call that, there's filter and stuff like that. There's also check valve. So all this, if we use equivalent length and represent, that means instead of putting various components, you just use the same methodology of increasing the length. And a very long length will means that you have different component inside. So that becomes a little bit easier to understand. Make sense? Make sense? Okay, so with that, right, I'll just draw a little bit of the method, then it can be a little bit easier. So assuming you have a valve here, and then a filter here. Okay, filter, a valve. So maybe let's say water flow from here to here, right? So instead of this is a distance, right? So instead of filter, right, we can say, assuming this filter is say 30 meter, or equivalent length. So this is the filter, it's 30 meter. Then this part, say AR, is like that. And the bar here say is another 30 meter. Okay. And maybe down here is B. So this is B. Okay, so now your water flow through, say maybe your water flow through at say 4 bar goes in. You pass through your filter, pass through your valve, say it comes back to about 2 bar, right? So it is equivalent to say that if you have a very long pipe, assuming this is very long pipe, then your water flow through a very long pipe, when it comes up here, it is 2 bar. So that's the meaning of equivalent equivalent length. Right? It's easier to understand this way, right? Right. Because you put this on how to calculate pressure loss. Sometimes very difficult. But if you put the whole length, the diameter is the same, then it becomes easier. Right? One straight line. Don't need to think. If there is another valve here, maybe I don't know, maybe some pump or valve here. Right? This is say 10 meter. And what you do, you just increase this another 10 meter. And then maybe here's still 2 bar, assuming. So this is the way we can design a piping. Right? So this is a way we usually use this way. Of course, there are other ways, but this is one of the most easier ways to look at things. Okay? Make sense? Yeah? Okay, so well, now it gets a little bit more complicated. Remember what I mentioned? The various fitting, right? LE divided by D is a virtual constant for the tight fitting, right? So let's see. Okay, for a 90 degrees, right, bend, the equivalent distance is about 30, right? So let's say you have a 90 degrees bend, right? It's about 30. LE or divided by D is about 30. But if you have 45 degrees, slightly less friction, right? So it's 16, about 16 for your L divided by D is 16. Make sense? So now you increase the bend, like sharp bend, the distance that is required will be much bigger, correct? Much longer. So the more it is, the more difficult. So a group valve fully open will give you about 320. A plug, all right, a plug valve two-way will give you about 17. So this is just an equivalent length to actually let us know what to do. So for fitting, the through is quite easy. If you go through the through pipe is about 20. If you have a straight line, it's basically about 10. Give him some roughness, right? And if there's a valve, diaphragm valve or butterfly valve, right, or leaf check valve, then the distance will kind of increase in short. Make sense? Okay. So let's see, 45 angle bend, right? And then various component. So ratio for reducer and enlarger. So you have a reducer, right, which is the external divided by the internal, right, give you 0.9. A reducer will give you about 3, right? And then if the external OD is divided by the ID is much smaller, then the reducer ratio will actually increase. Okay, so for example, like 100 mm go to about 80 mm diameter, then D over I is like 80 out, right? But by your internal, which is in, will be give you 0.8. Okay, so if you look at the opposite, right? If your incoming is 80 mm, and then your out is 100 mm, and then it goes down is about 80 mm. So imagine small goes to big, just like we go to our customs, right? QQQ very tough, then open up the door. So that usually the flow actually will be much more, right? So you're freer in the movement. Okay. Okay, so pipe sizing guideline, we have an enlarged You usually comes in, then we need to enlarge it, then you have a T, then you let it go out. So you usually have the enlarger here. So even for fan, right? You see, fan usually those better, what do you call that? Commercial building. You can see that the fan when we put a fan, right, in front of the fan or down this part of the fan, there's always an enlarger. Okay, if not, what will happen? The fan will then, when you suck the fan, right, then it will cause churning. So usually if you have like, if you go to say maybe our HDB flat downstairs, there's also what do you call that? People that's cooking, right? There's exhaust fan. Sometimes it's actually at the wall itself. And when you pass through, right, you will always hear some noise. So there's churning in a way. So have an enlarger is kind of to reduce this, to divert the air also. So there's one of the design. So this is a pipe sizing, huh? Okay, so we usually have a reducer, then a branch. So this is kind of incorrect design. You come in, then you reduce, then you T. So we try not to do that, but we try to do something like you go out, you enlarge it, right? Then you T off. Okay, so this is a base water plant we usually see, right? There's a cooling condenser side, then this is the evaporator side. Okay, so we'll do some example. Easier to see is this part. Okay, so let me just read through. So this diagram will have a one-sided chiller, and then the chill pump is identical. So what do we do? Right. So usually we'll start with one first. So assuming section one goes up, right? One is 20 meter. Once go to number two. Two is another 10 meter. Then it goes up. Okay. So section three is basically from this part goes out, right? It's another 4 meter. Okay. Okay, try again. Chiller section one is 20 meter. From here, chiller come out, go up. Here is 20 meter. Section two is say 10 meter. Section three, a small pipe, 4 meter. Section four is about 10 meters. So it's from here, right? Section four. Okay, it's return coming out. 4 meter. Five is where's five? Five is down here. Come out, branch out. It's about 4 meter. So this is one way that we bisection. That's a length. So for example, one is a gate valve, right? Gate valve is actually here. And then group valve is a dot, is a line with a dot. And check valve is like a Z but inverted. And strainer and two-wave modulating valve. So this is one way we look at it. So each section will be able to fill in the length. This is quite easy, right? And so now we have the pipe schedule 40. We usually try to use schedule 40 as usual. But of course, when the design guideline, you have various piping. So elbow is 90 degrees bend, welded, and then it's a square welded. So one AHU flow rate is 4 liters per second. Pressure drop is 20 kilopascal. AHU2 flow rate is 6. Pressure drop is 25. Chiller, we don't know the flow rate, but the pressure drop is 50. So design acceptable criteria for pressure drop is 100 to 400. Okay, so let's go back to the chart here, right? Chart here, pressure drop 100 to 400. Remember the yellow section? Yeah, can? So with that, we are now able to kind of design. So chiller will be approximately, right, about 10 liters per second from the chiller coming out, right? Yeah. So the flow rate for AHU 1 and 2 is 1 and 4, right? So this AHU 2 is 6. AHU 1 is 4. So 4 plus 6, 10 goes in, 4, and then 6 come out. So you have 10 here. 10? Yeah. So AHU 2, 6 goes in. and then come out 6. Then your ASU 4 is here, right? Goes up, come 10, return is 10, right? And then this is 10 liters per second. The rest of the length remains the same. One is standby, one is on duty. Okay. So this is a similar kind of a piping system that that shows the flow. Okay. So now we actually has 4 liters per sec. Okay, so we size bigger pipe, right? 6 liters per second. Remember the volumetric flow rate, 6 liters per second. We draw one line. And then the other one is 10 meters per second, right? Because it's down here. Going up is 10 meters per second. Then we draw another line here. So drawing another line, right? Then we want to find out the velocity, which is this side. Okay, which is this side. So you will cut between diameter of the pipe, which is about 80 mm. Okay, 80 mm and 100 mm. So the pressure drop will be in the range of 150 to 230. So this is kind of the range right now. So this is one way to actually size your piping. Of course, this is a manual way, right? Right now, usually we just punch in some numbers, it will churn out, but we still learn this method to kind of draw out. Make sense? Yeah? Not so super difficult, right? Okay, that's good. So similarly, this is for friction loss for commercial pipe, right? Then we take a look at this again. If this is 1.3 meter per second, 1.4 meter per second is down here, right? So if we push a little bit lower, right, up to here, still is about 1. This is 1.5. So it is still about 1.3, 1.4. If you push down the flow rate to 6 liters per second or 10 liters per second, right, and then you reduce the pipe a bit, that this basically will still give you about 150 to 230 Pascal per meter. Okay, very similar to the design, except that this is a little bit bigger. Yeah. Okay, so this is the confusing part. Actually, also not say very confusing. So we have section 1, 10 liters per second, right? 10 liters per second, diameter 100, right? So diameter 100 is by looking at here. Diameter 100, okay? So diameter 100 is here. Water velocity is 1.3. Diameter 100. Push it up. There, this is a typo. It's a 1.3, 1.3, or down here. Diameter 100 or 1.3. This is this value. Then for section 1, there's pipe, elbow, groove valve, gate valve, and T, right? How you see this? Let's take a look. Section 1, there's 1 elbow, 2 elbow, 3 elbow, 4 elbow, right? So take a look here. How many elbow? 4 elbow. Okay. Then gate valve. How do we see gate valve? Come out section 1. There's 1 gate valve here. Right. See the gate valve? So there's 1 gate valve here. Okay. So 1 gate valve, 1 groove valve, and then 1 T. So groove valve, again, we do the same. This is your groove valve, gate valve. Come out section 1, right? Before you go to section 2, there's a T, right? So you just put a T here. So this part is okay, from here to here. Okay, now we do the equivalent length. Equivalent length, right? So your distance, right? Your total distance for the length itself for the pipe bar is 20, correct? So step 1, the length is, the pipe itself is 20 meter. Elbow length, elbow is 4 times this 55 times 0.1, right? So where do we get this from? Okay, we have an equivalent length, which is this is elbow, right? So we go back to elbow. Yeah. So your elbow is 90-degree sharp bend 55 here. Okay. So then we go back, then we fill up the 55 and times your equivalent length. So in short, you go through and flow, then total equivalent length you add up. Then we have a pressure loss, right? Then your suction pressure, you have your total length times your pressure loss, then will give you a suction pressure. Okay. So this is like the section 1. Then we continue for section 2, section 4, H2, and add up together. But to do manually, a bit difficult, right? So usually we will, of course, use a spreadsheet to calculate. Okay. Right? So this is how equivalent length is kind of measured. Then we just calculate. Then after that, everything, right? The friction head, we can by calculation is H is pressure divided by your rho times G, right? Which is your density times gravity, right? Or then we are able to find your total pressure loss plus a safety factor plus your total. So this is your pressure loss plus a safety factor, then plus your friction head and static pump, then add up together from the previous page. So this will be kind of your total pressure. Make sense? So I may go through one section, but it is the replication of this because a lot of piping. Make sense? And okay, so example on the schematic also shows the condenser. Then we need to do pipe sizing about 10 liters per second, safety factor of 10%. So this is slightly easier. You just take a look at section 1. Where's section 1? So section 1, about 8 meter on the length, and then there is a group valve. So there's section 1. And section 2, of course, is up to here, about 6 meter. This is section 2. Section 3 is basically here. So we can still break down. Then we do the same, right? The 10 liters per second going in from chiller 2. Then when they combine the second chiller, right, there is 20 liters per second. So we do the similar approach, section 1, 10 liters per second, 100 mm diameter pipe. Then what is the pipe elbow? We count. Then we have the equivalent length. All this add up, right? And then have a pressure loss. And then calculate the section pressure loss. And with that, add it up together. Total carry forward pressure loss is about 45,000. And we calculate the pressure loss. And then that's how we end up with the ground pressure and of course your friction static and your pressure head. Okay. Make sense? Yeah, a little bit longer to calculate. Okay. Okay. All right. Okay. All right. So with that, right? Let's try. We should have a tutorial, I think. Yeah, ducting system. Yeah. So tutorial 3 ducting system is actually very similar to what we gave just now, right? So maybe what we'll do is I'll take a pause here, take a look at the piping system sizing again. Maybe take some time to read through a little bit and then let yourself understand a little bit more how this is kind of equivalent piping being kind of designed. Okay. While I pause for a while, you should be able to see there's a chart sizing and table, which I put in. Let me just turn to a learner's view. Under content, under sizing and table, you should be able to see a pipe sizing table here, right? When you click this, stop. Oh, okay, 1 second. Okay, are you able to see this in? Cannot, is it? Okay. Okay, let me just reduce again. Okay, from your, are you able to download this, or it's not? Is it working? Yeah. Are you able or no? We cannot see. Hmm. Okay, maybe I have not done the release condition. Okay, my bad. Okay.
You can see already.
Huh? Can see already. Yeah. Okay. Why? Okay, I also don't know why. All right. Either way, there's the pipe sizing table here. Yeah, pipe sizing table. So there's the Excel file. And then there's a sizing table, which is like this one. And then the final one is this picture here. Should be at least these three files you will need to kind of take to actually do the pipe sizing part. It makes sense? Make sense? Oh, too tough. Very tough, huh? Okay, let me try. Okay, maybe we take a few minutes to read through again, and then you figure out what is how to bring it down, how to do sizing using the chart. Okay, a bit confusing at the beginning, but you can take out your paper and pen or paper and pen, then you try to follow the what do you call that, the lecture note, and then see if you can actually collate. And then we try the lecture first, then we can then try the tutorial. Okay, we take a few minutes to kind of go through your this particular lessons, lesson 8, right? Yeah. We go through the piping part and understand a little bit how it works. After a while, I think should be quite okay. Not so super difficult, but at least I'll give a try. Okay? Okay. Yeah. All good? and give a try. Use this time to actually see where it goes. Go through one more time, is it? Sorry, can you repeat again?
Go through section one time first. Then I think we should be able to replicate whatever you do to the next section and so on.
Okay, can. Just 1 minute. Okay, let's try one more time. Okay, so for example, 7.19 example. We do one more time. Section 1. Section 1 is from here, chiller, come out, and all the way up to here, right? That is section 1. Section 1 is 20 meter. Okay? Now, okay, all good, right? And so section 1 is 20 meter. Then it has how many? 1 elbow, 2 elbow, 3 elbow, 4 elbow, correct? So we do this first. So we go to section 1, and then from the AHU come out 1 is 4 liters per second. AHU come out of the water is 6 liters per second. So the material is for schedule 40 steel, elbow 90 degrees bend. Then there's a T square T sharp bend. Okay, so design acceptable range is still 100 to 400 Pascal per meter, right? So this is okay. Okay, so what we do is come here, parameter 100 to 400 pressure drop. The yellow color is the acceptable, right? Right. Section 1 is chiller going because AHU 2 is 6 liters per second. AHU 1 is 4 liters per second. So total is 10 liters per second. Okay. AHU 2, 6 liter. AHU 1, 4 liters. 6 plus 4 equals to 10. Okay. Can So we do this first. Then 10 liters per second. Remember the chart. Below, down here, is 10 liters per second. Okay. We draw one line straight up. Okay. Then our pressure drop 100, and our pressure drop is, if we are using, this is 100 meter diameter pipe. 100 meter diameter pipe will give us approximately pressure drop of 150 Pascal, which is still okay, right? Because it's 100 to 400. So this is good. And then our flow, our velocity will be approximately about 1.3 meters per second. See, this is 1 meter, 1 meter per second. This is 1.6. So somewhere in between here is 1.3. Okay, so this point is okay. Yeah. Okay, so go this place first. Flow rate 10 liters per second. Correct. Given diameter 100. Right? Just now we just try, right? Down here, 10 meters per second. In order to match, to fall in the yellow column, we size at 100 mm diameter. Okay? 100 mm diameter will be here. Okay? Then the fourth step is the velocity. 1.3. Where we get what this 1.3? Try again. Down here, right? 100. The diagonal light blue, if you cut it up here, this is 1.3 meter per second. Okay, so that's where we get this 1.3. Okay, I stop here for a while. Is this okay? So far? Okay.
It's like bigger the number is small.
Which part? Sorry.
Actually, no.
Okay.
I can only put three.
This one is it? Okay. So this one is actually 1.3. This part are correct. Then this is 1.4. This is my bad on this one, my bad. This one is exactly the same. I think my bad. This one the lecture note is strong. It's 1.3, this is 1.4. Yeah. Okay, up to this step, section 1, 10 liters per second, 100 mm, and 1.3 here down here, okay? Can Then pipe 20 meter, so very easy. You carry forward 20 meter. Elbow, got 4 elbow, right? Just now we calculate 1, 2, 3, 4, 4 elbow, 4 elbow. Then you calculate the rest lah. Okay, this part okay, right? 1 elbow, right? Where did we get this 50, 55? 90 degrees sharp bend, right? 90 degrees sharp bend, L times D, sorry. Yeah.
We will use this specific for everything.
So if it's specified 90 degree sharp bend, then we use 50. Right? Sorry, 55, my bad, 55. If it's specified that is a threaded elbow, then it's 30. Yes, that's correct. That's correct. Yes. Okay. So L divided by D is 55. So we have down here, this is L divided by D is 55, right? But your D is 100 mm. L divided by D is 55, then you times another 100 mm, which is 0.1 meter. Then with that, you get an equivalent distance. Then all this, you do the same, you add up, you have your total equivalent length. Okay, this part, okay? Okay, then not finally, 2 more steps. One is your pressure loss. The pressure loss, just now we measure here, my bad about this one, if you can correct. The pressure loss, 100 meters per second, diameter 100 mm. Pressure draw is you push it to the y-axis is 150 Pascal per meter, correct? 150 Pascal per meter. Then we put down here 150 Pascal per meter. Okay. Equivalent length you have already. Just now we calculate the elbow, right? Times 4 times 55. L divided by D times your D, which was distance. Then all this add up will give you equivalent distance. Equivalent distance times pressure drop will give you the total or the section pressure loss, which is in this case, everything add up 77.5 times 150 will give you a pressure drop about 11,557 Pascal. Okay. All good? All good, Okay. Okay, well, I do one more, Gate valve, one gate valve, right? One gate valve. So one gate valve, where do we get this 7.5? From the table. In gate valve. Where's gate valve? Gate valve 7.5. Okay. Gate valve 7.5. And we go back again. 7.5 times diameter 100 mm, which is 0.1 meter lah. Then you have your add this up again. So group valve is 320, T is 23. Same method. Add this all up together will give you this number. Okay. If you can do until here, then that's pretty good already. Then all your total suction loss, then you add it up together. Okay. And maybe give a try like Those which is okay, maybe show of hand, those is okay. Or the class not okay. Okay, those not okay, put out your hand. Those not okay, put out your hand. Not okay. Yeah. Not used to it yet. Okay, okay. Okay, maybe you try like the next 5-10 minutes, you try again. Yeah, give a try. No hurry, no hurry. Just take it easy, give a try. So not okay. Yeah. This group okay, yeah? Yeah. Is it too complex? Okay, give a try first, give a try first. Oh, too tired. Tired, huh? So this is the last topic already. Yeah. Luckily, this is after the test. Mm. Okay, can? Okay. Okay. One more, little bit more. So we learn how to do section 1 already, the pressure loss. Then we do the rest. Then you add up together. Everything add up together. Will give you a total pressure loss of 135,579.6 Pascal. So we put in a safety factor of 10, usually 10. Add this up together will give you about 149,137.6 Pascal. And so from this, one more step is there is a friction head. There's a calculation we need to do. Your friction head is equals to your pressure divided by rho G, or rho G head. Pressure equals to rho G H. Pressure is equals to rho G H, right? That's why H is your head pressure, then density times your gravity. Pressure comes from your total pressure, which is 149, divided by density, which is 1000, times gravity is 9.81. So will give you 15.2 meter. 15.2 meter, right, will give you your friction head, and then, right, yeah, and then basically this will be your friction head, and then you put it in as giving additional a little bit more of then giving you addition, then your pump head will be about 15.2. Okay, make sense? And make sense? So if you look at usually pressure is equals to density times gravity times your height, right? Height is your head. What is head? Head is basically, let's say this is the water, this is the height. So usually we call this part the head. So assuming this is say 10 meter, your water is here, pressing down, right? So what is the pressure here? Pressure will be equal to your rho, density of it, times the gravity, 9.81, right? Because of gravity, times 10, which is 10 meter, which is your height or your height. Okay, so roughly, assuming this is 1000. Okay, how much is this? 1000, 10,000. Sorry?
98,000.
Yeah, 98,000, right? 98,000 Pascal usually. Can? So assuming we try to have the water here, but now instead of 10 meter, we have 100 meter. Okay, so the pressure here of 100 meter will be same 1000, right? Gravity times 9.81, and instead of 10 meter, 100 meter, what will be this number?
981,000.
Right? Which one is a bigger pressure?
The right one.
The right one, because same idea, right? Yeah. So so this is basically the pressure. Now you understand this, right? So inside this equation, we work opposite. So from here we understand the theory already. So from this theory, what's the next step? Is to find out the height, right? Because why? We have your pressure divided by rho times G, right? This pressure is your friction pressure, right? Or your static suction pressure loss, because there's a pipe, right? So then you will find out what is the head. So now, what opposite? You have all your piping very, very long, correct? Now I want to push, right? I want to push my, I know my pressure here already because it's equivalent pressure. Now I want to find out what will be the head of this. So assuming I know the head, which is assuming I don't know this first, but I know my pressure. I know my, okay, assuming I don't know this, let me finish this. So I don't know my height. So I want to find out, but I know my pressure. See, my pressure is assuming 98,000 Pascal. Assuming, right? So what happened? Your height will be equals to your pressure divided by rho times G, right? Pressure is 98. And then 1000, 9.81, that will give you 10 meter. So I now know the pressure. I will now need to, and then now I know there's a 10 meter. So what can we do with this 10 meter? Remember I shared with you how to select a pump. A pump will require this particular to overcome this pressure. So I have to select a minimum pump of a pump head of a 10 meter. So you tell your supplier, hey, I need a pump. My head is, I need it more than 10 meters. So put a little bit more, a pump here of 11 meters. Then it will give you a pump that is 11 meters. So I put my pump here. When I start the pump, water will pump, probably pump up to about 11 meters, assuming then water will come out here. Okay? So the minimum pressure, to find out how much your pump you need to design, we need to know the pressure. With the pressure, we will be able to find the head. With the head, we are able to tell your pump vendor or your pump contractor, right, how much and what type of pump I need. Make sense? And yeah. And okay. Any specific questions? Okay, we take a okay. The head is horizontal. Now let's try. So assuming this is water, then I have a pipe here. Assuming this is also 100 meter. What will be the distance of the pipe? Then assuming this is straight is 100 meter. What will be the distance of the pipe? Yeah, so assuming this is 45 degrees, so this is about 125 meter, 100, yeah, approximately, yeah, correct? So distance of the pipe is longer, but what will be the head? The head is still the same. Okay?
Uh-huh.
Make sense?
Yeah.
Yeah. Okay. Maybe we break from here, then go back, just try out a little bit. After this, probably like tomorrow or by next week, I'll send the solution for tutorial 3. Then you can just try out. Okay?
Okay.
Can. Right? So this part, high chance during the common test, we'll see how, but this part, probably I'll give a one liner or maybe 5 rows, then you can calculate, not calculate, then fill up, and then as part of the exam. Can. Not so difficult. Can. Okay. All right, everyone, all good? Huh? The pipe is the easiest one. The duck is a little bit more confusing. Yeah, duck, you have to find the area, then you need to size that one. A bit more confusing. Okay, pipe is the most basic entry. Okay. Okay. All right. So there's nothing. Enjoy the holidays with the assignment and all the assignment you have. No choice. Yeah, student. Yeah. The quiz for the fact, yeah. Before the common test, before the 11th of August. Can. Okay. Hey, yeah. Some of you haven't finished the tutorial. Please quickly do submit. 1 and 2. 1 and 2. 1 and 2. Tutorial, you know. You know where you have submitted or not submitted? Yes, very good. Okay. Okay, see you. Okay, see you. Yeah. Yeah.